So this is 5A, center of mass. So any system that has multiple objects, like this one with Blake and Angela, they have a center of mass. And all that means is the average position of the mass. So I'm actually going to start out here before we get to the problems that they actually ask us to do, to give you an example of how to find the center of mass. So it's sort of a way to think about like students in a class getting a score. Like how many students got 70 points and how many students got 80 points. And when you add up all the points possible by that all the students got divided by all the possible points, you would get the average for the class. So here's how you find the center of mass of something. So the position of the center of mass is equal to this. We give each mass, each kilogram, you can think of it as like a score. So let's say there's social distancing here and there's 6 feet between the two of them. So now let's figure out where the center of mass is. So Blake, let's say, is standing here at 0. We'll call this 6. So Blake has 75 kilograms, and they get a score of 0. So all 75 kilograms of him we'll just pretend is basically right over that line and has a score of 0. Now let's take into account Angela's mass. She's got 50 kilograms, and she's got a score of 6 feet there. So that is all the points, so to speak, that the mass got. The total mass of the system is 75 plus 50, so 125 kilograms. So now we can figure out the average position of that mass. So 75 times 0 is 0, 50 times 6 is 300, so 300 over 125, and that gives you 2.6. So the center of mass is 2.6, so I'll just estimate it right about there, away from the 0 point. That makes sense when you think about it. Blake's got more mass, so if they were equal masses, then the average position of the mass would be right dead center at 3 feet. But because he's got a little bit more mass, he's got to pull that average towards him a little bit. So 2.6 feet away from him would be the average position of that mass. All right, now let's get to the questions that they ask. They want a free body diagram on each of them. And so, and draw them relative lengths there. So Blake here will draw a force of gravity. I'll draw it 1, 2, 3, 4, 5, 6, and I'll call that the force of gravity on Blake. And then 1, 2, 3, 4, 5, 6 up. We'll call that the normal force on Blake. Got to be equal and opposite because he's not accelerating in the y direction. And then I'll just go 1, 2, 3, just because I feel like it, for the tension in the rope acting on Blake. What about Angela? Well, she's got a little bit less mass. She's only got 2/3 the mass, so 2/3 of 6 would be 4. 1, 2, 3, 4. So her force of gravity line would be a little bit less, but her normal force, 1, 2, 3, 4, should be equal to the force of gravity on her. But remember back when we did dynamics, the tension is the same everywhere. You can also think of Newton's third law. If there's a force on Blake this way, then there's an equal and opposite force on Angela the other way. So 1, 2, 3, I'll draw the tension in like that. So there is the free body diagram. Next thing they want is it says, from the following 4 statements about the situation above, place a check mark next to the statement if it is completely true and provide justification. If it is partly true, correct the statement. And if it is false, cross the statement out and provide justification. All right, so first thing, only Angela moves relative to the ice. Nonsense. There's a force on Blake. Can you even see that mark there? There's a force on Blake, so Blake will accelerate. He will move. And the mass, the rope, will also move as well. It doesn't have any mass, so it'll start to move there. B says the magnitude of Angela's acceleration is less than the magnitude of Blake's acceleration. No, that's not true either. This is the problem. Because Angela has less mass, acceleration, remember, is force over mass. So Angela's acceleration is more than Blake's there. Or you could have switched Angela to Blake there, and that would have made that statement correct. Let's look at the next two here. So, just before they meet, Blake's speed is less than Angela's speed. That is true, because Blake is going to have less of an acceleration, So they're going to hit at the same time, so his final speed will be less than that. While the students are moving, it says in D, their momentum vectors have equal magnitude and direction. So you can see that this is probably the incorrect part right here, but let's think about it. They are going to have the same force on them, according to Newton's third law, and that force will act for the same time. If they have the same force and time, they will have the same impulses on each other. And if they have the same impulses, they will have the same change in momentums. The only thing you need to remember here is actually they will have equal and opposite forces. So they will have equal and opposite impulses, and they will have equal and opposite changes in momentum. Next part says, where do the two students meet? The students meet at, well, let's think about the force on the system. There is no external force on the system, and therefore there will be no acceleration for the system. The system's acceleration will be equal to 0. So where can we think of the whole system as being? Right here, right at the center of mass. So they'll meet, whoop, right there, because the system itself won't accelerate at all because there's no net forces on it. So they will meet at the center of mass. All right, let's do one more center of mass problem here. So this one, in some of you at home might be missing this paper here, but follow along here. It says Carlos, who's got a mass of 50 kilograms, stands on the far left edge of a 100 kilogram stand-up paddleboard. The board is 6 meters long, as shown in the diagram below, and slides across the surface of water with negligible friction. Well, that's not actually true at all, but whatever. On the diagram, show the location of the student board center of mass. So the system is the student in the board. Then draw what the system will look like after Carlos walks to the other end of the board. On this second diagram, mark the location of the student board center of mass. Okay, I'm going to do another, basically thinking of it as a score to find the center of mass here. So the position of the center of mass will equal, let's see here, Carlos is 50 kilograms, it says. So he's got 50 kilograms, and he's at the 8 meter mark here. So those 50 kilograms will get a mark of 8. And then we got to take care of the board. The board's own center of mass will be right in the middle. It will be as if all the board's mass, we can average it out to be right there at the 11 mark there. So it's got a mass of 100, and it's at the 11 mark there. So when we go to add all of this up, when we work it out, oh, and we got to divide by the entire mass of the system, which is 150. So this will be 400, and this will be 1,100 over 150. So this will be 1,500 over 150. So the center of mass works out to be 10 meters. So right there is the center of mass of the student board system. This also makes sense from another point of view. Since the board is twice the mass of Carlos, the center of mass should be twice as close to its center of mass. So here we're 1 meter away from the board center, but we're 2 meters away from Carlos's center. So that makes sense from that type of reasoning as well. So now he's going to walk to the other end. Now here's the thing, there's no external forces on the system, so there'll be no acceleration of the system. That means that the center of the mass still has to be here at the 10 meter mark. It can't move at all. So, and think about, it's still going to have the same role as we did up here. Because the board is more massive, twice as massive, it's got to be only 1 meter away as opposed to Carlos's 2 meters away. So that means the center of the board is right here. So the board, 1, 2, 3 this way, and then 1, 2, 3 this way. So there's my 6 meter board right there. So the center of the board is now at the 9 meter mark. And then we'll draw Carlos, he's at the other end. So he's standing here, he's at the 12 meter mark.